Log on, tune in, find out. Another good idea from Cambridge.
Before we start, if I could just mention that the posters for the poster session are now set up next door. And what we will do in respect of that is to go in there during the coffee session, sort of starting this afternoon. So do, when you get your coffee, do wander in and have a look at the posters, and poster people do be there to talk about your posters, and we'll repeat that on other occasions during the week. Okay, so it's my pleasure to welcome our first speaker, Frédéric Le Gall, from École Nationale des Ponts et Chaussées and the INRIA MAC Group, are both based in Paris, who will talk on the title that we have here.
Thank you very much. I'd like to thank the conference organizers for the invitation. So what I'm going to present is a work that we did recently with Xavier Blanc, Ronan Kostawek, and Claude Lebris on stochastic homogenization. And our focus is really from the practical viewpoint, in the sense we want to, or we are aiming at making stochastic homogenization more practical from the algorithmic viewpoint. Okay, so I will start to explain the difficulties of stochastic homogenization. I will start by reviewing the easiest setting, which is the periodic homogenization, because from the contrast between these two settings, you really understand where the difficulty comes from. Okay, so for those of you who are familiar with homogenization or stochastic homogenization, please bear with me for a couple of minutes, and then we'll enter the heart of the subject. Okay, so homogenization for the periodic setting has been known for a very long time. So I consider here the easiest case, which is just a scalar equation in divergence form, and I've got here a periodic tensor so it's scaled with this 1/epsilon factor here, and so there is no problem, of course, for the existence of u epsilon, but the question is what happens when epsilon goes to 0. And so we all know that when epsilon goes to 0, then u epsilon converges to a solution, a function u star, which happens to be solution of the same kind of equation. So it's again an equation in divergence form with an effective tensor r star, which does not depend anymore on epsilon. So from the practical viewpoint, it's very interesting because we could use mesh sizes that are reasonable here to compute the solution of that one. And the effective matrix A star here is given by these two formula. So what you do first is you look at the last line, which is, so you solve this equation for this W function here for any vector P. So it's an easy game because by construction this W is periodic. Okay, so you look for the solution of that equation with W periodic, and so you only have to mesh a bounded domain, which is just a unit cube. Okay, so you mesh that, you mesh this bounded domain, you compute this W, and then you insert this W into this average formula, and this gives you the A star, which is the effective tensor here. Okay, so from the numerical viewpoint, it's easy. First solve that equation on a bounded domain, and then compute this average. And then off you go, you've got the A star, and if you wish, you can compute U star solution of that guy. Okay, so far so good. But here what we are interested in is random material. So here are two examples. Here it's, say, a composite with fibers. So fibers are more or less arranged on a periodic array, but it's like you were looking at a very periodic material through random glasses. So the radius of each of the fiber is now a bit different. Its properties are now a bit different, and this difference is random. Okay, so the randomness comes from the position of the fibers or the properties. And here it's a more extreme case where you've got again, it's a heat conduction problem with a tensor which is piecewise constant. Okay, so pink or black. All right, and so this is what we want to consider. Okay, so the setting of stochastic homogenization is a bit more complicated than the periodic case, so let me go over it quickly, and I will stress in the next slide what is important to keep in mind. Okay, so what we want to have is that we wish that the material or the properties of the material are statistically equivalent, in the sense that we want the properties there to be equivalent to there, okay, on the average. And the way it is formalized is that you introduce a probability space with the set of randomness, and you assume that you have a group action on that preserve the probability measure, and which is ergodic. Okay, so all right, say you've got this, and now you've got an important property is that here, so previously we assumed periodicity, okay, for the periodic setting. Now we are going to replace this assumption by stationarity, which is formalized in this way, and the consequence in terms of understanding, capturing what it means, is that because of this assumption on the properties of the material, first the properties at x and x plus k of the material have the same probability distribution. So statistically they are the same. Okay, both are random, but the distribution is just the same. And now if you look at the mean or the expectation properties at one point, you recover a periodic function. Okay, so it's random around some periodic function. And why this setting is useful? Because you have this ergodic theorem, which plays an important role in the theory. So you remember for periodic function that a periodic function weakly converges to its average. Okay. Now, for in stochastic homogenization, you've got the same kind of result in the sense that this function here converges. Well, it's not exactly its average in space, and also on the randomness in the sense you take the expectation. Okay, and if A happens not to depend on the randomness, you are exactly back to the periodic setting, and you converge to the standard average of the function over the unit cube. Okay. All right. So all the setting aims at having this averaging property for a function, which plays exactly the same role as in the periodic case, the fact that a periodic function converges to its average, okay, in the weak limit. Okay, so how does that work? What's the theory for stochastic homogenization? Okay, so we again take the heat conduction equation with a tensor A here, which is stationary. Okay, so just the assumption about similar to periodicity. And again, what happens is that this u epsilon converges when epsilon goes to 0 to u star, which is a solution now of a deterministic equation. A star will be deterministic. Okay, so here we exactly have the same result as for periodic homogenization, but the point is how A star is defined. A star is defined as, again, an average, as in the periodic setting, but in addition you put an expectation, and the function W here, which used to be solution of a deterministic PDE on the unit cube, now solve this set of equation. So you recover the same equation, but the point I want to stress is that the main difference between that system of equation and the previous system in the periodic case is that this W now is defined on the whole space R to D, okay, and you have to solve so a PDE in a unbounded domain. Okay, so from the theory it's very nice, and from the practical viewpoint it's a nightmare because this equation is set on RD, and so you've got to do something in practice to compute an approximation of this W here. And once you've got the W, you will hopefully be able to compute this average in space and randomness. Okay, so this is the setting of stochastic homogenization, and the issue comes from this fact. Okay, so how people do in practice? Well, yep. Okay, so you've got it almost surely, and in L2 strongly and H1 weakly. Okay? And almost surely with respect to the randomness. Okay, so you need to do something to compute an approximation of that problem, okay, because it's posed in unbounded domain. And a standard discretization scheme is to introduce a truncated domain, so Qn, which is minus n to the d, and to solve the same equation as before, but now with periodic boundary condition on the domain Qn. Okay? So you are back to a compact domain, but of course the issue is that morally n will have to be very large to make something reasonable. Okay? Okay, so you have this W which solves now this equation, and you can compute it, say, with finite element method. And once you've got this W and x by n, then you compute an approximation of the effective matrix by the same formula as before. And because this W depends on n, you've got a star which depends on n. Okay? And one artifact of the numerical discretization is that this A star here, n, now is a random number. It's not a deterministic number anymore. There is no expectation here, but an average over the domain. Okay, so this W is random because A was random, and this A star is random. Okay, so, yep.
Sorry, what was the Q on the previous page?
Q is the unit cube.
Okay.
Okay. So Q is always the unit cube. And what you do here is you say, okay, this expectation here, because I've got an ergodic theorem, you can replace expectation by an average over the full space. Okay. That's the idea. Okay. So this guy here would be the limit when n goes to infinity of 1 over qn, the integral of qn of that guy. And so you're making first this approximation of replacing the expectation with that, and second, this function is a solution of that guy and not the exact function. Okay, so there are two approximations there. Okay, and okay, so you've got an effective tensor which is a random number. So from the okay, so you know it's work by Bourget and Piatnitsky that this effective matrix will converge to the quantity you wish, A star, when n goes to infinity. So the size of the domain goes to infinity. But in practice, this is, I mean, you've got some limitation, and in practice, you will work with some given, hopefully large n, and this is what you can do. Okay, and in practice, so it's very hard, of course, to go to the limit n goes to infinity. All right. So this number is random. So there are two artifacts because of this numerical truncation. First is that you've got a systematic error in the sense that if you take the expectation of that guy, it's not the one you're looking for. Okay, and we're not going to address that issue now. What we are going to address is, okay, since this number is random, there is variance, and what we would like to be able to do is to compute the expectation of that number more efficiently than with a standard method. Okay, so now our aim is not exactly to compute A star, but to compute the expectation of that guy, assuming that this will be close enough to A star. Okay. In practice, what you have is, even if this is your aim, here is what you get as one entry of the matrix A star as the domain here Qn grows. Okay, so in abscissa, this is the size of the domain, and in the y-axis, this is one entry of A star, and these guys here are confidence intervals. So you do many realization of A. You compute for all these realizations, you compute A star, which is a random number, and from that bunch of random number, you compute, well, the empirical expectation and a confidence interval. Okay? And this is the results that you get. And so you see that the convergence, for instance, with respect to n is very slow, and the confidence interval is quite large. Okay, so what we are aiming at is, can we make a method that reduces this confidence interval? Okay. And so that computes more efficiently the expectation of this A star n. All right. So what we are going to use for that is a classical method in the for probability, or classical method for those who know, which is the technique of antithetic variable. So let me explain it on a very simple example. I want to compute the expectation of a function of a uniform variable. Okay, so I've got a uniform variable u. It's a random variable distributed in 0, 1. I've got a function f. I want to compute this expectation. Okay, so a basic Monte Carlo method would be to draw realizations, independent realizations of the random variable, say 2m, and to compute the empirical expectation, which is just the sum of these guys, and well, relying on the law of large number and the central limit theorem, you know that this guy, when m goes to infinity, is a good approximation of the expectation of f of u, and the confidence interval is basically governed by the variance of this guy. Okay, and so the antithetic variable methods is to say, okay, we are not going to consider 2m independent realizations. We are going to consider m independent realizations. Here are they. Okay, and for the next ones, for the m next ones, we are going to choose this random variable, 1 minus um. Okay. So if um is uniformly distributed between 0 and 1, then 1 minus um is also uniformly distributed between 0 and 1. And so you can make the argument that these two quantities both converge to the same quantity, which is the one you want to compute. And they've got the same cost because they both of them use 2m evaluations of the function f. Okay, you've got 2m f is here, and you've got 2m evaluations of the function f here. Okay, so the question is, okay, they've got the same cost. What do you gain from that? Do you gain here an estimator whose variance, where the noise is smaller or not? Okay, so here are the two estimators. You compute the variances of these two guys, and what you find is that the variance of this new estimator is the variance of the previous one plus this covariance term. So it's okay. So it's more efficient if this variance here is smaller than that one. That is to say, this guy is non-positive. All right, and so these antithetic variable techniques, which relies on saying, okay, I'm going to associate to each u, I'm going to associate 1 minus u, works if you've got this condition. And now there is a standard theorem in probability that says, okay, if you take a function, if the function you are using here is non-decreasing, then indeed the covariance is non-positive, and then you've got an estimator with a variance which is smaller. Okay, so if you are trying to compute a function, the average of a function f which is non-increasing, then this technique of antithetic variables gives you an estimator with a smaller variance. Okay, so for an equal cost, you've got something which is more accurate. Okay, and so all what we are going to do is to use exactly this idea in stochastic homogenization setting, saying, okay, now I've got an input which used to be u here, which now is going to be the initial random field of my material, okay, the properties of the material at point x and for the randomness omega. And the output that I'm trying to compute is just the effective matrix, okay? And so you've got, but now the chain that takes you from the input to the output is very complicated because it amounts to solving the corrector problem, finding this W function on the truncated domain and compute the average and so on and so forth. Okay? But from very far away, it's exactly that. Okay, so what we are going to do is each time we see a random structure in the input, we are going in parallel to compute the antithetic structure. Okay, so assume that the field you were working with is just a field which is piecewise constant. You remember the drawing with the pink and black squares. Okay, so assume that this AK takes value pink and black. Okay, now I've got this field, and I'm going to consider the antithetic field, which is just constructed. So here is a picture. You've got the initial field here, and you consider the antithetic field, which is just amounts to saying, okay, each time I see black, I put white in the right material. Okay, Each time you see pink, you put, each time you see white, you put black. Each time you see black, you put white, right? And you can do this for more complicated laws. If now, so here it's easy because you've got just two values for the conductivity. Now, if you've got conductivity that are can take a continuous set of value between alpha and beta, what you do is just you take the symmetric with respect to the average. So here I make a drawing where you've got the effective conductivity between alpha and beta. Here is your initial value for the left material, and what you compute, what you take as the right material is just the symmetric B with respect to the center. Okay. All right. So now you've got this antithetic material, this negative material, if you wish, and what you do is, well, instead of considering 2m material from the left column here and computing for each of these guys the corrector and then the effective matrix and then computing the empirical average, so which is to do that. Instead of doing all of that, okay, we are going to consider m of this guy, and for each of them you associate the antithetic structure related to it, okay? So you've got the initial field. You've got a realization of the initial field. You consider the antithetic realization, so which is just the negative of it. And for that negative of it, you run all the program of homogenization, solving for the corrector, taking the effective matrix, B star, and considering as so an estimator, well, this half sum of the two effective matrices, okay? All right. So both this quantity have the same cost because you need to solve for each of them 2m corrector problem. That is the problem on the supercell Qn, the big one. They are convergent in the sense, okay, in the limit of infinite realization, they converge to the right quantity. And now, okay, the efficiency is again governed by the fact that covariance should be non-negative. All right. Okay, so let's see how it works from the numerical viewpoint. So here is an example of material. So it's piecewise constant, and the value at on each of the square can take any value between alpha and beta, and they are uniformly distributed between these two guys. So in the x-axis is the size of the domain Qn, the y-axis is one entry of the effective matrix. The red curves are the one with the standard method, so no noise reduction, okay? And so, well, again, you've got some large confidence interval here. And the green curves are the one obtained with the variance reduction. So exactly with the same cost as the red one, but where you play this trick of taking the negative material, okay? And so you observe that the size, the width of the confidence interval is much smaller or smaller in the green case than in the red case. Okay. So okay, so we can. Okay, so I'm going to skip this. Okay, so here what I looked at was on the numerical example I just looked at was the easiest case in the sense, okay, the value of the field is piecewise constant. This is completely uncorrelated from one cell to the next one, okay? And so we did a numerical test on more complicated cases where we looked so at correlated fields, so when the fields, the input fields at one point and another point are correlated, but we know the correlation structure, okay? We know the underlying uncorrelated structure. We did also some tests in the anisotropic case, so where the matrix is not just the identity. Here in all what I discussed the point of getting an estimation of the effective matrix, A star or A star n, or of its entries. You could be also interested in the eigenvalues of that matrix. You could be interested in the eigenvalue of the associated operator minus divergence A star grad associated to that one. So that would be the vibration modes of the structure. Or you could also be interested, well, in the homogenized problem, which is solving this in the end. Okay? And so for all of these quantities, we checked numerically that, okay, the method yields a good result. So now just one point on, this will be my last slide, about understanding what's going on, okay, here in this setting. So I'm going just to discuss the 1D case. In the 1D case, you can do all the computation analytically. And so the effective coefficients turn out to be, so it's again like a harmonic average, okay, as discussed this morning by Asir, except the fact that you take also the average in terms of expectation. And now if you do the truncation, then this is the exact formula that you end up with. Okay, and now if you take the very simple case where A is again constant and piecewise constant on each cell, then this A star n is computable, and this is just the harmonic average of the value that you see in your supercell. Okay, so you solve the problem in the supercell minus n to n, and in that cell you see this value, and so the A star n is just the harmonic average of the value that you see in the cell, in the supercell. And what it turns out is that this harmonic average is a increasing function of the value. Okay? And we've seen earlier that this antithetic variable technique works for functions that are increasing. Okay? So in this 1D case, it works because of that. And so for the A star, for instance, for the eigenvalues, it works because the eigenvalues is a non-decreasing function of the matrix itself. Okay? All right. And so you can do also some proofs in the 2D case or higher dimension. And basically what you rely on is monotonicity properties of homogenization. So if you've got a field that is larger than another one, this is also true for after homogenization. All right, so what I presented is so this approach that we have tested in many 2D situations, and in some cases, so 1D and some 2D situations, we proved that it indeed reduces the variance. You should keep in mind that this is a very simple equation. This is just a linear equation in divergence form. Okay, so what we wanted to focus in these variance reduction, so from all the other points we took something very simple. Okay, and so here are some papers that we wrote on this method. If you're interested with that, I thank you for your attention.
Okay, so I think we have time for 1 or 2 quick questions. Yeah.
Under what condition on a covariance matrix you get any computational savings there? I didn't follow. And also, from the covariance, when you know, there are various ways you can parameterize. Like, does it depend on that? Or
Okay, so
isotropic, anisotropic, does it anyway affect?
does there any way of
Affect?
No, it does not affect. It does not. The fact that it's isotropic or non-isotropic does not affect the point. In the correlated case, again, so we looked at that, but we knew what was the underlying uncorrelated structure. Okay, so we used that uncorrelated structure to propose the antithetic material.
Is it like something like KL expansion? What do you mean by underlying?
No, we knew that, okay, the value on these two cells are correlated because they are the sum and the difference of two random variables that these two random variables are uncorrelated. Okay, they are a function of uncorrelated variables. And so we play the trick of the antithetic variable on these uncorrelated variables. If you give me a field which is correlated, but you do not give me why is it correlated or where, then we didn't test that for it yet. But
if I give you a Gaussian field and you can do spectral expansion of that, and can you do?
Okay, we have not tried that yet, and we'll see.
I had well, several questions, but one is so this lemma you're using,
Yep.
about the variance reduction. Is there a version of it which quantifies how much?
No, that's a good question, and no. No, the answer is no. So you just know that it reduces the variance, but you don't know by how much.
Okay.
You don't know by how much.
And in your numerical examples, it looks like it's reducing the variance, but also changing the average as well?
No, it does not change the average. It's just that the average is well computed on empirically. So there is a but okay. In terms of variance reduction, we obtain. I mean, the computational savings were about say 6 in terms of computational time. Okay, so for the same accuracy, you've got a computational time which is divided by somewhat 6.
Okay. Thank you. Okay. So thank the speaker once again.
Thank you.